Section 3.2, Techniques of Differentiation. So as promised, we're going to get a few techniques which will allow us to compute derivatives way more quickly than we could before using the limit definition. So yeah, let's get into this. So the first rule we're going to look at is the constant rule. It turns out that the derivative of any constant function is just equal to 0. All right, and some other notation which is going to be relevant is this. So if we're taking the derivative with respect to x, so d dx of some constant c, this is just going to be equal to 0 no matter what that constant is. So yeah, this d dx, what that means is take the derivative with respect to x. That's what this notation means. Take derivative with respect to x. Okay, so if we're ever taking a derivative of a function which is constant or has a term which is constant, that's just going to go to 0. The next rule is the power rule. To find the derivative of x to the n, what we do is we multiply by the original exponent. So we multiply by n, and then we subtract 1 from the exponent on x. Okay, so that means, writing this out, the derivative with respect to x of x to the n is just going to be equal to n times x to the n minus 1. So that's what we mean when we say multiply by the original exponent n and then subtract 1 from the exponent on x. Okay, let's do some examples here. So we want to find the derivative of all these functions here, and we're going to do it using these two properties that we just learned. We're not going to use limits at all, which should be welcome news because those limits can be pretty time consuming and can take a lot of steps. So if we want to find the derivative of f of x equals -9, since -9 is a constant value, right? It's just some real number. The derivative f prime of x is just going to be equal to 0. Okay, and to sort of qualify this, if you think of the graph of f of x equals -9, what this graph looks like is it's just a horizontal line down here at -9. It just looks like this. Okay, so since the derivative gives us the slopes of tangent lines, if we pick any point on this line, say this one right here, doesn't matter what the x value is, what's the slope of the tangent line at that point? Well, the tangent line just mimics the slope of the graph at that point, and we can see that every tangent line is going to be horizontal, meaning every tangent line is going to have a slope of 0. That's why this derivative should make sense. It's just the function that outputs 0 no matter what x is. Okay, you could also run this through the limit definition and you would get the same result. So, just wanted to sort of qualify that answer using a graph. I'll let you play around with the limits if you're curious about that. Next function, f of x is equal to x to the 4th power. So according to the power rule, since this is in the form x to the n, where n is equal to 4, the derivative f prime of x should be equal to, okay, the process is bring down the old exponent 4 and then subtract 1 to get the new exponent on x. So that means that f prime of x is going to be 4x to the 3rd. That was so fast. Now, and I'm not encouraging you to do this, but imagine if we tried to calculate this limit, using the limit definition, x plus h to the fourth power minus x to the fourth power over h, taking that limit as h goes to 0. The only way that I'd be able to evaluate this limit is I would have to take this and multiply it out. So x plus h times x plus h 4 times. I haven't even started multiplying yet, and I'm already tired of writing. I'd have to FOIL these two together, multiply those two together, and get a big, something starting with x to the fourth and ending with h to the fourth. That would take so long. That would take so long to do. And here I was able to calculate that derivative in 5 seconds. Now for the square root function. So we found the derivative to the square root function. That was one of the last examples in this last section. Sorry, I'm just scrolling up here. Here's what we had to do to get this derivative. We had to plug into the limit. We had to multiply by the conjugate and go through this long process of getting that derivative. 1 over 2 root x is what we landed on. So it turns out there's a much, much quicker way to do this, because we can rewrite the square root of x using an exponent. I can rewrite this as x to the 1/2 power. And writing it in this way enables us to apply the power rule, which we just learned up there. So the derivative f prime of x. To do the power rule, we'll just bring down the old exponent, 1/2, and then subtract 1 from that old exponent, so 1/2 minus 1 up here. And we'll be left with 1/2 times x to the negative 1/2 power, right? 1/2 minus 1 gives us negative 1/2. And this is the same thing as 1 over 2 root x, right? The negative exponent flips it into the denominator, and the 1/2 power makes it a square root. So we just landed on the same result. However, this time we did it using the power rule, and it took us about 20 seconds. Okay, part D, f of x, we're looking at 1 over x to the third power. So it wouldn't be on this page if we couldn't apply either the constant rule or the power rule to take this derivative, because those are the only two techniques we have aside from the limit definition. So this isn't a constant function, so I don't think it's going to be that rule. How can we get the power rule to apply to this function 1 over x cubed? In other words, how could I express this as x to the n power, where n is some real number? Well, I could just flip this up into the numerator and make this x to the negative third power. A little weird having a negative exponent there, but let's see what happens. If I do the power rule here, I would bring down the negative 3, and then I would have x to the negative 3 minus 1, right? Subtracting 1 from that exponent. So I'd be left with negative 3 times x to the negative 4th power, or I might just write that as negative 3 over x to the 4th. So there's our derivative. Even if our exponent is not an integer, right? In part E, we have f of x equals x to the 1.7. That's a really random exponent, but it turns out we can still apply the power rule. This is just going to be f prime of x equal to 1.7 x to the 0.7. I'll just do it all in one step there, right? Bring down the old exponent, subtract 1 from the old exponent to get the new exponent. There's our answer. Okay, so this power rule can be applied in a whole bunch of different situations. and it can save us a whole lot of time. So let's move on, talk about a couple more of these sort of elementary rules of differentiation. The next one is the constant multiple rule. If c is any constant, meaning, for our purposes, any real number, and f of x is a differentiable function, then so is c times f of x. And the derivative of c times f of x is just equal to c times the derivative of f of x. Or we could just write that as c times f prime of x. And what this means is we don't really have to worry about constants when we're taking derivatives of functions that, might have a term with a constant out in front. We can kind of just ignore it and take the derivative of the part involving the variable. All right, and then sum rule. If we have, to use kind of the same language we used when we were looking at limits and the rules of limits, the derivative of the sum is equal to the sum of the derivatives. Okay, so this means that we can differentiate term by term. So if we have a whole bunch of terms lined up in a function and we want to take the derivative, we don't have to worry about dealing with them all at once. We can take them one at a time. So in example 2, we want to differentiate a few of these functions here. We'll start by looking at this polynomial here. So 5x to the fourth plus 3x squared minus 7x plus 9. Okay, so if I want to take the derivative, I'm going to write out some of these steps here. We want to take the derivative of this whole thing, right? So f prime of x is going to be the derivative of this whole entire function, 5x to the fourth plus, blah, 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 up to 9. So what these two rules tell us is that I can take the derivatives of each of these term by term, and I don't have to worry about the constant values. So this is the same as 5 times the derivative of x to the fourth plus 3 times the derivative of x squared minus, and so on. Okay, so I'm not going to write these two steps every time, or probably ever again, but I just want to indicate how we're actually applying the sum rule and the constant multiple rule to get this derivative. So let's do it. So 5 times the derivative of x to the fourth, I'll bring down that old exponent 4, and then I'll subtract 1 to get the new exponent, which will be 3. Okay, and then plus 3 times 2 times x to the first power, so just using the power rule again, minus 7, right? That just becomes minus 7, and then plus 0, the constant. When I take the derivative, it's just going to go to 0. So my answer, f prime of x, is going to be 20x cubed plus 6 x to the first power minus 7. Great. Let's try another one here. So we want to take the derivative of f of x equals 1 minus 1 over x plus 2 over root x. So I know I can take these terms one at a time. I just want to ideally get these into a form where it's obvious what I'll do to take the derivative using some of the rules that we already have. And 1 over x, it would be convenient to write each of these in the form x to the n, so that I could use a power rule, and I think I can do that here. I can rewrite this as 1 minus x to the negative first power plus 2 times x to the negative 1/2. All right, the negative sign indicates that this should be in the denominator, and the 1/2 is the square root. And I want to write it in this form because now I can take the derivative of each term using the power rule. So here we go, f prime of x, it's going to be equal to 0, right? Derivative of 1, or any constant for that matter, is 0, minus, bring down the -1, that's the old exponent, and subtract 1 to get the new exponent of -2. Okay, and then plus 2 times, bring down the -1/2, subtract 1 from -1/2, I get -3/2. Okay, and I can simplify this a bit. This will become plus a positive. This, you know, the 2 and the 1/2 can cancel. That's just going to become a 1. So f prime of x is going to be, I won't write the 0, so I'm just going to have x to the -2nd. I'm going to write that as 1 over x squared. And then minus x to the -3/2. I can write that as 1 over x to the 3/2. I could write it that way. Or I could write it as the square root cubed, right? Because the 2 in the denominator gives us that square root. The 3 in the numerator is just, you know, a third power. So I think this is a totally reasonable way of expressing this answer. If you wrote that as 1 over x to the 3/2, I wouldn't have been mad at that. Very good. Part C, we have a function which is a product of two polynomials, the product of a quadratic and a linear function. So how can we get the derivative of this using all the rules that we already have? Well, we don't have a product rule yet. I wish that it was so simple as just, you know, take the derivative of this and then multiply it by the derivative of this. Unfortunately, the product rule for differentiation is not that simple. But we'll get that product rule very soon. But for now, we don't really have much of a choice other than to multiply this out. So to sort of rewrite this in a form which is differentiation friendly, I'm going to multiply this out. You could do the FOIL method or distribute that, however you like to do it. I'll get 3x squared plus 2x cubed minus 3x minus 2x squared. Okay, so that was just my sort of first inner outer last procedure. And now let's see, does that simplify at all? Yeah, I have a couple of like terms, the 3x squared and the negative 2x squared, so I'll simplify a little bit. I'll write this as 2x cubed plus x squared minus 3x. Okay, so I just move things around a little bit to get it in that general form, you know, descending powers on x. And that looks pretty good to me. So now I'm ready to take my derivative. So over here, I'll actually do the differentiation. F prime of x will be equal to, and look, I'll do this one kind of quickly, right? So let's take the derivative of this first term. I know I'm going to bring down the 3, subtract 1 from the exponent, multiply the 3 with the 2, I'll get 6x squared. This next term will just be plus 2x, and the last term will just be minus 3. Okay, so definitely show as much work as you need. You want to be able to communicate to me as, you know, the person grading your work that you know what you're doing. Don't be too jumpy with trying to just get straight to the answer. But with some of these derivatives, you'll really get in the swing of things. You know, just bringing down that 3 and multiplying it by the 2, and you know, we can knock these out pretty quickly once we get some experience. Next problem, here we have a quotient, which doesn't really simplify too much. We don't have a quotient rule yet. We are going to get one, but we don't have it yet. Unfortunately, it's not as simple as just, take the derivative of the numerator and the derivative of the denominator. There's a little more to it than that. So we'll have to find a workaround for now. I'll want to rewrite this in such a way that the power rule will be applicable. And here's how I can do that. I can split up this fraction. Remember, if we have a sum or difference in the numerator, we can break it into multiple fractions. I'll write this as root x over x minus x over x. And, for the sake of simplifying this, it might make sense to rewrite that root as x to the 1/2. Okay, so simplifying this expression a little bit using our properties of exponents, this is going to be x to the negative 1/2. I just did, 1/2 minus 1. Subtraction rule there. Minus x divided by x is just 1. Okay, so keeping in mind that 0 is not in the domain of this function f, but writing it in this form, we should be able to apply a power rule and a constant rule to get this derivative pretty quickly. So f prime of x will be equal to, bring down the negative 1/2 and then subtract 1 from that exponent, so I'll get negative 3/2. And then minus the derivative of 1 is just going to be 0. So our derivative, f prime of x, is going to be negative 1 over 2 x to the 3/2. You could write it that way, or you could write it, the way we did in that previous problem. Square root of x cubed. I'm relatively flexible on how you write your answer, but I usually try to avoid negative exponents in my solutions. Great. So just a few examples there, getting used to applying all of these various rules of differentiation that we have. Example 3, we want to find an equation to a line tangent to this function. We have a 4th degree polynomial, x to the 4th plus 2x squared minus 1 at this point 1, 2. All right, so we've done a few of these already. Remember, our answer is going to be in the form y equals mx plus b, right? We're trying to find the equation of the tangent line, so it's going to be something in this form. First, we want to find that slope m. Find the slope of that tangent line, so m, which is m tan, tan. And the way that I can find this is taking the derivative of my function and plugging in my a value, which in this case is going to be 1. Okay, and notation for this, it's going to be the derivative of our function x to the 4th plus 2x squared minus 1 evaluated at x equals 1. This is just a bar here. This is a notation. This just means the derivative evaluated at x equals 1. So the derivative is going to be 4x to the 3rd plus 4x plus 0, right? Because that constant value goes to 0 and we take the derivative. And we just want to evaluate this now at x equals 1. So let's plug 1 into this. And I'm going to get, 4 times 1 cubed plus 4 times 1. So it's just going to be 4 plus 4. I'm getting 8. All right, very good. Let's now use that. So now we gotta find b. So now let's use the fact that m is equal to 8 and x equals 1 and y equals 2 to find b. Just reminding you of how this process goes. We can either plug into y equals mx plus b. Right, so we could plug into that and we would get 2 equals 8 times 1 plus b. And, you know, subtract 8 from both sides, I get b is equal to -6. Okay, and putting those two things together, I have that the equation of the line tangent to that function at the point 1, 2 is y equals 8x minus 6. So we're able to do that way more quickly than, you know, the first time we did one of these problems using the limit definition. And this is a pretty serious function, you know, 4th degree polynomial. So using these new rules of differentiation, there's really incredible tools at knocking out derivatives quickly, and, you know, we can get tangent lines lickety-split. Example 4, this is a really common calculus problem. Find all the values of x on the graph of f, this given cubic function, at which the tangent line is horizontal. So we want to find where we have horizontal tangent lines. So what's going to be important here is, what is the slope of a horizontal line? Well, a horizontal line just looks like this. You know, the rise over run, the rise is 0, the run is 1, right? Like for each one step to the right, we don't take a step up. So the slope of a horizontal line is just going to be equal to, you know, rise over run, 0 over 1. It's just equal to 0. So we want to find where is this derivative equal to 0. Okay, so I'll say i.e. where is f prime of x equal to 0? Okay, don't make the mistake of plugging 0 into the derivative. Sometimes I see that. Remember, we want the slope to be 0, and we're looking for the x values. It says find all the x values. So we're solving for x in this problem, not substituting in for it. So let's find this derivative. This is going to work out nicely. I'll bring down the 3, which will make a big 1 with that 1/3. So the derivative will just be x squared minus 6x plus 5. Constant term goes to 0. So now let's set that equal to 0. X squared minus 6x plus 5 equals 0. This is a quadratic equation. Let's see if it factors. That's going to be the easiest, quickest way to solve this. Do we have two numbers that multiply to 5 and add to -6? I think we do. I think that -5 and -1 are going to do the trick. Right? They multiply to +5, add to -6. So the factored form will be x minus 5 times x minus 1. So now setting each of those equal to 0, x minus 5 equals 0, x minus 1 equals 0. So it looks like our solutions are x equals 5 and x equals 1. So these are the two points at which, supposedly, we have horizontal tangent lines on this graph. So I encourage you to type this into your graphing calculator and see what type of graph you get. Okay, and I'll kind of spoil it for you here. The graph, it's a cubic function. It's going to roughly have this shape. It's going to roughly have this shape. And right here, this is going to be where x equals 1. And right here is going to be where x equals 5. Okay, and if we look at the tangent lines at those points, they're going to be horizontal lines like that. All right, and I wanted to point this out, kind of this graphical phenomenon with horizontal lines, horizontal tangent lines. Oftentimes, at horizontal tangent lines, we will have local maxima or local minima. Okay, so this is going to be a really helpful thing in some future sections. Finding where we have horizontal tangent lines will be really helpful in learning about functions and their graphs. Okay, but please type this into your graphing calculator and be able to sort of check your work. Make sure that it makes sense graphically that we have horizontal tangent lines at 1 and 5. All right, next up, we're going to talk about nth derivatives. Because some of us love derivatives so much that 1 is not enough. Sometimes we want to take more than 1. Maybe we want a second derivative. Maybe we want a third derivative. That's what we're going to find in example 5. And we'll find out later that we find these not just because we love taking derivatives, but they actually give us more information about functions, which is really, really helpful. We'll see that very soon. So the nth derivative for any positive integer n, the nth derivative of a function is obtained from the function by differentiating n times. The nth derivative is written either like this, like if we're using the prime notation, f with a little n up there, or sometimes we'll use tick marks. We'll see that in the example below, of x, or if we're using this other notation, we might write d n f over dx to the n. Okay, so that's like the nth derivative. Okay, in many cases, finding multiple derivatives is not a huge deal, because oftentimes terms drop off as we take each derivative. So let me show you what I'm talking about in this next example. We want the third derivative of this 10th degree polynomial. Good thing we have our power rules, right? Because this would take a literal lifetime to find the derivative using the limit. I don't even know if it's possible. But with our power rules, the first derivative, I'll just bring down that 10. I'll get 50x to the 9th, subtracting 1 to get that new exponent, minus 30x to the 4th, minus 27. All right, and then that constant 4 just goes away. So that's our first derivative. Now let's find the second derivative. I'm going to denote this with f double prime. All right, and we're just going to differentiate again. The hardest thing about this is multiplying 9 times 50. So we'll get 450x to the, now we're on to the 8th power, minus 30 times 4, I think 120, x to the 3rd. And the negative 27 drops off because that's a constant. All right, and then we'll find the third derivative by just differentiating one more time. There's f triple prime. 8 times 450, I got 3600 x to the 7th power minus 360 x squared. Okay, if you got tired of writing the primes, you also could have written f triple prime like that of x, right? That's just the other notation. So there it is. We're done. We don't have to go any further than this. We just wanted the third derivative, and there it is. Okay, so nth derivatives, third derivatives, not necessarily too bad. Just taking the derivative of the derivative of the derivative. Okay, and that's it for this section. Up next, we're going to talk about the product and quotient rules, which I promised you a couple examples ago. So I will see you in section 3.3.